Welcome to another seminar on another webinar on the series of Buildchain seminars. Today, the title of the webinar is Safer and More Resilient Built Environment with a Buildchain System. My name is Bostjan Brank, and I will moderate this seminar. So we have 5 speakers today. The first speaker will be Professor Juan Chiachio from the University of Granada, and he will talk about the big picture of the digital twin concept. So he will explain how to connect the real system, the real life system with a model in a quick mode. And this will be presented in the framework of the Buildchain system. So please, Professor Juan Chiachio, do your presentation.
Thanks, Bostjan. Well, first of all, let me share my screen. Can someone confirm that I am sharing the screen?
Yes, it's fine.
Okay, good. Well, first of all, thank you for the invitation to this webinar. My name is Juan Chiachio Ruano, Associate Professor of Structural Engineering at the University of Granada. And I will be talking about digital twin and how this technology, in the context of structures, of course, and how this technology can be embedded into our Buildchain technology or platform. Well, first things first, I need to explain or to say something of what a digital twin is and why is it important. A digital twin, formally speaking, is a digital replica of a physical reality. That's it. So, for example, we think on a structure. You can see this picture at the left. This is a laboratory scale structure full of sensors, different type of sensors than the accelerometers, etc. And then we have a digital version of this reality in our computer, where we can reproduce not only the mechanical behavior of the structure, but also we can reproduce the position of the sensors, where the sensors, in which points those sensors need to provide data, etc. Okay, so this is, formally speaking, what a digital twin is. It's a very simple concept. Now, in the context of structural integrity, the importance of the digital twinning technology is because it aims to automatically carry out damage diagnosis and damage prognosis. And here is let's say, the utility of this technology. More specifically, we aim at try to lead to intelligent or digital management of our buildings and our civil engineering infrastructure using this technology. So this explains why it is important and the reason talking about this today. Let me explain a little bit more about the reasons or let's say the objectives of this technology in the context of the project, the motivation, let's say, of this technology. Well, here I have highlighted 3 aspects. One of them is the obsolescence of our buildings and our civil engineering infrastructures. You know, in Europe, at least, many or most of our existing buildings and civil engineering structures are near the end of life. So this is a reality that you can observe just in our streets, in our cities. Also, this industry, let's say the building engineering, civil engineering industry, typically leads to poor or inefficient maintenance strategies. For example, some visual inspections or some calendar-based maintenance activities instead of condition-based, instead of, let's say, data-driven activities. So this leads to poor or inefficient maintenance strategies, leading to this obsolescence of the infrastructure. Also, we are living in the era of sensors, in the era of the digitalization, let's say. And this digitalization technology is relatively cheap in relation to the huge maintenance cost or restoration cost of the infrastructure and the buildings. So this also called for, for this technology, for this digital technology to help with the management, with the obsolescence and management of our infrastructure. This provides, let's say, the big picture of the motivation, the reasons why we are talking about this today. Sorry. Let me go more in depth about the architecture of the digital twin. What the ingredients are in this particular technology. Here I am showing different aspects, different ingredients, but this can be collected into three main blocks. The first is the simulation block, learning block, second one, and the management block. Let me go to the first one, the simulation block. The simulation block is, let's say, a technology, computational technology, where we can simulate our physical reality. This means, for example, finite element modeling, computational models of the structure. This means, for example, BIM, building information modeling technology. This means SHM, structural health monitoring. All these are part of this simulation block that we are highlighting here. The second important aspect, the second important block for this technology, for this digital twin technology to be ready, is the learning block. By learning, we mean all these artificial intelligence techniques, uncertainty quantification techniques, inference techniques, so that when we have data, we can learn from this data, we can extract conclusions, we can make the model more sophisticated and more accurate. This is our learning technology. Finally, we need a management block. Why management? Let me go, let's say, a little bit more, let me do this zoom in for the management of the digital twin. We see a digital twin as an expert system using this management block. In this particular case, we are proposing Petrinets as a technology to control the digital twin as a robot, let's say, and we control the flow of data, the functioning of sensors, how frequency, how long we are taking data, how we control the communication between the data and the servers, when we need to target a modeling server to do a particular computation, etc., etc. All these aspects are controlled as an expert system, let's say, and this is the last management block for the digital twin technology that we are proposing in Buildchain. Going more in depth about this architecture of the digital twin that we are proposing, basically we are talking again about two realities. We have our physical reality, our physical entity, which is basically we have our structure here. We have sensors, we have actuators, we can have microcontrollers, which basically are microcomputers doing small operations on board of the structure. This data is then transferred into a particular servers or different servers where we do different activities, like, for example, post-processing of the data, modeling activities, analytic activities, etc. And this creates the digital entity, all these, let's say, computational computer activities creates the digital entity of the digital twin, together with a front end where we can visualize the results. We can see different aspects. For example, we can see the recordings of the data, or we can see the diagnosis or the prognosis of the system, etc., etc. So this just to to provide a picture on this technology. Well, these aspects can be found on a recent article that we have published. So those of you who may be interested on knowing more about this, you can see the reference. A little bit more in depth on the architecture, on the big picture, let's say, of a digital twin in the context of the structural integrity. Well, first of all, we have a structure, let's say a bridge, or we can think on a building. And this building is, we have several sensors on it. So we say it is a monitored structure, okay? Those sensors are providing data, and this data goes to pass through an acquisition system, okay? And this acquisition system push the data to a server. This data server is just a computer, let's say. In the particular case of structural integrity, most of the time we are looking at vibration data, let's say ambient vibration data. And there will be other speakers now today talking about how to convert this raw vibration data into something more meaningful to extract information about the structure. But here, just I wanted to show the big picture of all the aspects here. So we have this data server where we collect the data, we post-process the data, and we put this data into a database, which is there just available for when it is requested or needed. Then we will have a master server, which is another computer, which is requesting information or frequently about whether or not there is data in this data server. And when there's data in this data server, there's a token, and then the data is requested is pushed into this master server. The master server has different activities. Of course, the first one is to this external synchronization service, but also something important is that we are proposing this fast inference service where when we collect the data, we check whether or not the data is relevant for the purposes of the digital twin. Most of the times, the data is not relevant because it's in normal life, in the structure, in a building, things are, let's say, normal, so we don't expect damages all the days. So most of the time, the data is not relevant. So this fast inference service just neglect the data if it is not relevant. But in the case that the data is relevant for the purpose of the digital twin, then this master server first communicate with the acquisition system to say, hey, I need more data, more about this, because there is something else that I need to understand. So first request more data, modify the acquisition system. For example, if we have a number of 10 sensors, out of them only 2 are continuously working, then after having known that there is something in the data, we can propose changes into this acquisition system to ask the rest of sensors to provide information. And then another aspect that we trigger is that we push the data into a modeling server. And this is a server, is a separate server where we do, let's say, heavy computations. The first thing that we do is to, first of all, is to try to understand the data in the context of a finite element model or a model of the structure. And this is carried out using a particular technique, which is called Bayesian model updating, which is a very technical aspect that there will be speakers talking about this today. Once we cross-check this information with the model, we understand whether or not there is something new into the structure, and this updated information is pushed down into the master server, which produces the information in a front end, or just push this information into the Buildchain platform. So this is somehow the let's say the big picture of the digital twin technology in the context of Buildchain. In summary, what we need is, first of all, we want to create this self-attending digital twin technology to automate the data management and the model updating of structures. This is the first need. Second, using the Buildchain technology, we will create a trustable digital twin data infrastructure, which will be enabled by decentralized knowledge graphs. By trustable, we mean just collecting and storing the relevant data, relevant information for the purposes of the digital twin. So the type of data that we will use, first of all, we need the building geometry, the monitoring scheme, how many sensors, location, configuration, etc. Of course, the sensor data. If we are using, for example, accelerometers, we will use ambient vibration data. If we are using any other, for example, tensometry, we will have displacement data, etc., etc. So all this data, together with the metadata of those sensors, for example, sampling rate, frequency, etc., all this information is useful for us, is requested, is needed. The type of data that we will produce and we will push into the Buildchain platform is, well, there are different type of data that we will produce, but one of them is, first of all, is the optimal system, the optimal sensing configuration. You can imagine in a big building or a big bridge, we don't have just 2, 3 sensors. There is a system, there's a sensing system. So the configuration of this system is complicated. So one of the aspects that we need to produce and to information is about how to configure it in real time or almost real time this sensing system, plus the information about the diagnosis and prognosis of damage of this structure. Just to finish my presentation, this is just a publicitary aspect. All this information can be found, or part of this information can be found in a recent article. I am happy to share it with those of you who might be interested. If you write the title in Google, you can find it because it's open access. And that's it. I am open to questions, of course. If you don't want to make questions here, you can just write me an email to share information with you. And in principle, that's it.
Thank you, Professor Chiachio. Now this presentation is open for discussion. We have a first question from George Dorzanos, and the question is: can some building blocks, slide 13, of the digital twin be facilitated by a BIM software? For example, in the model server part for end part.
You can repeat. Can the model?
The second sentence.
Yes.
Can some building blocks, slide 13 of the digital twin be facilitated by a BIM software? Yeah,
of course. Yeah. Yes. Yeah, this is one of the aspects that I haven't mentioned, but of course, all these activities, all this technology can be facilitated by BIM or inserted into BIM. So this, in fact, this is something that we are discussing in the context of Buildchain consortium, how we are embedding this into BIM. But yes, of course, yeah.
Okay.
Something important I want to say. The type of, or let's say, the degree of definition that we need for our geometry, for, let's say, for structural mechanics purposes is different than the degree of refinement of the geometry that is needed for BIM. But of course, from BIM we can create this. BIM can be a facilitator, let's say, in summary.
Well, can I have another question? We know that even if you have a large number of sensors for example, on the bridge, it is very difficult to know or to get from the data information if the bridge is damaged and where the damage is. So how can you comment on that?
Yeah, you are totally right. Typically, we differentiate between local damages and global damages. Global damages means, for example, a change into the material properties, general material properties. For example, a decrease of the stiffness of some type of materials, for example, concrete or steel is more difficult to see this particular decrease of stiffness. But in in practice, what they want to mean, these global damages can be easily seen by this sensing system. When we think on local damages is more difficult to reach by, for example, accelerometers. In this case, it's more convenient to use, for example, ultrasound sensors localized on the particular hot points where we expect damage. For example, if we are expecting corrosion in some particular joints, the strategy is to install, for example, ultrasounds or other type of sensors on those hot points, and then the rest of the bridge, the rest of the building is monitored with accelerometers to capture the global damage. But yes, here this opens another aspect, which is the differentiation between global and local damage. And for local damage, if we want to target local damage, we need a very dedicated sensing system. Most of the time is out of the scope of this at least of this approach. I am thinking, as let's say, as a hypothesis, that we are reaching global damages of the structure.
Mm-hmm. Thank you. I guess there are no other questions. So
Thank you.
If there's thank you so much, Juan. Now we can go to the second speaker. Second speaker is Dr. Uros Bohinc, who is an expert on experimental mechanics or experimental procedures for structures. He's coming from Slovenia, from the Slovenia National Building and Civil Engineering Institute. He will talk about the experiments on the structures that are needed to construct the digital twin. Please, Uros.
Hello, thank you for the introduction. Thank you also for the possibility to speak a little bit about our experiences with structures, the experiments that we've done so far. I will try to shed some light on that part of this webinar. So we'll talk about the model analysis specifically, and the experimental methods that are used to identify the model parameters. Let me share first the screen. First, maybe it's a general perception that structures are more or less static. So we don't normally think of them as responding to the environment through vibrations, through dynamic movement. But this is, of course, the case, although the movement of the structure is usually very minute, and it's hard to detect, and it's hard to see it with the naked eye. Normally, if you see the movement with the naked eye, that normally means that something is going very bad. We will try to see how modal analysis, the analysis of the dynamic behavioral structure is done experimentally. So first, let's break up this words modal analysis and try to see what it actually means. We already said that the structures vibrate and they behave actually dynamically. The response of a structure, the dynamic response of a structure, can be described or qualified by normal response, which are called modes, and these typical vibration modes have their specific frequencies. Usually these are the modal parameters that we are after. So we want to define the dynamic behavior of a structural response by pinning down what are the frequencies of these mode shapes, how the mode shapes look like, what is the damping ratio, and so on. So modal analysis in general is a technique used in structural engineering to identify the dynamic behavior of structures. There are many experimental methods that can be used to get them. But first of all, we have to ask ourselves what's good is it? I mean, how can modal analysis help us with understanding the structural response? How can that be used in structural health monitoring? Overall, the model analysis and the knowledge of how the structure behaves dynamically to external loading tells a lot about the rigidity of the structure, of the way the structure functions, and by monitoring, for instance, changes in natural frequencies of structure alone, we can say something about the evolution of a damage. So maybe a decrease in natural frequencies can indicate the presence of a damage. So can also the change in damping ratio, if the damping ratio of a certain vibration mode gets higher, then normally that indicates the presence of a crack or some other type of damage. If we are able to monitor the evolution or change in mode shapes as well, we can maybe also say something about or determine the point where the damage is present. Modal analysis can be helpful for the purpose of structural health monitoring, and I will in the following try to present some cases where we used experimental techniques to determine the model properties, we try to study how these properties can be used for SHM. Experimental methods, techniques. There are many of them which can be used. Basically, they can be divided into big classes. One of the classes is are experimental methods which use artificial and controlled excitation of a structure. So we have to excite the vibration of a structure and then measure the response. If we do it in a systematic way, then we can deduct not only the natural frequencies of the mode shapes, but also the mode shapes as well. And this kind of approach is very useful for structures which are easily accessible, but sadly that are not normally civil engineering structures, because these are quite big. So the experimental methods which use controlled excitation are more or less used in mechanical engineering for smaller structures like machines, airplanes, and so on. But in civil engineering, we have to rely upon methods which where the excitation is not known. So we just measure the response of the structure and try to deduce the dynamical properties of a structure just by studying the response, not knowing the excitation. So in this class of methods, there is operation model analysis, or sometimes called ambient vibration testing. The first one that I spoke about recently is impact testing and modal testing using modal hammers or shakers. There are, of course, also alternative methods which are more suitable to smaller structures, which are quite common in mechanical engineering. So there you can use laser Doppler vibrometry to study the vibration mode of a speaker, for instance, or a housing of a machine, or digital image correlation can be used to acquire the modal shapes of a structure, and that's the DIC can that is the digital image correlation can actually be also used for civil engineering structures. But these methods are more demanding in terms of instrumentation, and therefore we try to implement more conventional methods, and this that will be presented also through a use case is experimental model analysis, where an impact hammer is used to excite the structure. So this is the control excitation that I talked about. So using a hammer which has an instrument, a device, a load cell installed, which can measure exactly the force applied to the structure, can be then used to excite and also to measure the excitation of the structure. That can be done also, as I said, with a shaker, but using a shaker is more cumbersome. So the other class is operation model analysis, where the excitation is not known, and the excitation normally comes from the environment, and that can be, I mean, there are various kinds of excitation around, whether it be wind, traffic, some machinery operating nearby a structure, or micro tremors, earthquakes, and so on. So there is a lot of excitation sources around. So usually it's not a problem that the structure wouldn't be excited. So there is always some dynamic response. It's only the fact that this response is usually very minute, and it's hard to detect. So you have to use high sensitive instrumentation. Normally, these are some accelerometers, or even strain gauges can be used, displacement reducers, and so on. So you have to take care of the measurements, which have to be done really precisely. So I will now present two cases where we used both methods. So the first one is where we applied the experimental model analysis using the impact model hammer to excite the structure is shown here. This is like a toy structure built in our structural testing lab. This is a very simple steel structure, but still not trivial. So there is a response which can be modeled with a numerical model, and we try to match the results of the numerical model with our experiments. So we used a model hammer shown here on the left picture at the bottom to excite the structure at different points. So you can see here on the right, we used a number of different accelerometers to measure the response. There are uniaxial accelerometers, 3-axial, high sensitivity ones. So a lot of instrumentation since we wanted to capture as much as possible. This is just a screenshot of the software that we used to record the response of a structure. With this on the left side, you can see a simplified sketch of a structure with some notes indicating the location of the measurements. That is the points with a red circle around. So we measured only at 4 points, but we excited the structure at all the blue points. So we were able to reconstruct the model shapes in this mesh. The model identification starts with inspecting the Fourier transform of the vibration signals. So you can identify there in these signals some resonance frequencies where the structure responds with normal modes. Once you get these modes, then you can identify model shapes. I'm sorry for this picture. Maybe it's not very, of course, it is not very clear since it's on a black background, but still, this is the result of the analysis. You can see the modal frequencies written and the modal shapes in different projections. We were able to match these results with the results of numerical model. So numerical model of the structure was made, and the model shapes were computed and then compared to the experimental results. As you can see, if you take a look at just the first mode, this one, the basic deflection shape is captured with a numerical model quite well, but the frequency of that mode shape was not computed very accurately with the numerical model. So that means that there are some assumptions in the numerical model which are simply wrong and need to be corrected. And Blaz and Noémi will talk about ways how to use the experimental data to match, to validate the numerical model. So the second example that I wanted to share with you was a measurement of a footbridge, which we did last summer. Since this structure is obviously quite big, it was not possible to excite it with the model hammer. So we had to rely on this excitations from the environment. Usually the traffic was just good enough for this excitation. You can see on the left, on the right here is the monitoring station with a computer and the display of the acceleration. Here we have the disposition of all the measurement points that we taken on the bridge. So again, we used a number of different accelerometers to capture the response. 3-axial accelerometer here in the middle, high sensitivity for the reference accelerometer, and uniaxial accelerometers, which we had to move through the along the structure and while we repeated the measurements several times. So by inspecting the frequency spectra of the response, we were able to immediately identify the vertical vibration shapes and also the horizontal ones. Here in green, we've shown only the response in vertical direction, in blue horizontal one. So you can see some of the frequencies correspond to horizontal vibrations, and the other ones to vertical. We ran a simplified analysis, which gave us a basic deflection shape of first few modes, and here are the results shown on the right. So red and black line represents two girders which run along the bridge. So you can think of this result as a view from the side of the bridge. So actually, we got some pretty good results with it. I can maybe share some also an animation that was done in a different software. So I'm not sure if you're now seeing that. It's okay. We can animate the mode shape of the structure, and we can compare it with numerical model. And yeah, you can gain meaningful information from the experiments, and especially if you are able to validate the numerical model of the structure by experimental data, then you gain a powerful tool which can help you through the life cycle of a structure to help monitor it very closely, to predict the maintenance and so on. Thank you for your attention. Yeah, this is the end of my talk. If you have any questions, yeah, feel free to ask. Bostjan, muted. Yeah.
Thank you, Uros. At the moment, we don't have any questions, so I will start with questions. So if you have sensors on the bridge, for example, or on the structure, and we know that the structures, they change the dynamical properties slightly due to the climate, for example, due to the temperature. So is it possible that from the sensors which continuously monitor the structure, you get the dynamic properties in real time? So is it possible that you do that?
Yeah, I mean, if you monitor the response of a structure continuously, so you perform this kind of measurements not only in one measurement campaign in one point of time, but do it continuously with a permanent installation, then you will see that the results, of course, vary as the temperature.
Yeah, no, but I'm just asking: is it possible that you get the solution like in real time? So yeah. Every 5 minutes you get a new data for dynamical properties. It's not a problem to do that.
This can be done. Actually, apart from the commercial software available, there are nowadays also open software solutions which can do that. So we are currently in the scope of another research project investigating this option to install permanent monitoring, and then which will be able to produce continuously the results of the model analysis, and that results can further be used to, I don't know, trigger some alarms, to trigger some actions.
Okay. Thank you, Uros. I don't see any questions at the moment, so maybe they will be at the end of the webinar. And So we can go now to the third presentation, which will be given by Professor Noémi Friedman and her PhD student, Blaz Kurent. So Noémi Friedman is coming from the Institute of Computer Science and Control from Budapest, and Blaz Kurent, he is located in Ljubljana, Slovenia. So please, Noémi. I guess you're muted, right?
Yes, we handle that. Sorry, we are working on one machine now, so we are trying to collaborate, and this is kind of new with the video, not with the collaboration. Okay, so I'm going to talk about how to use in general data that we can observe on a built structure. And I will try to answer the following questions in this talk together with Blaz. First, in general, what we can do with the data, what kind of data we can use, and how we can use it to improve safety and resilience of our buildings. The second question, which I am going to address today, is how to make explainable machine learning models to predict and understand structural behavior. So this is a purely data-driven approach that I will explain, and then I will just shortly introduce the idea of a hybrid model. So combining our simulation models that you have seen in these presentations. You saw in one presentation what are those different elements. So some of those elements we will explain in more detail of this system. So this last section will be about how to combine data with, for example, a finite element model. We call these webinars as the Tell It to Your Mother webinars, turned by Uros. And the idea was to find common language, because in this Buildchain project, there are many disciplinaries presented in the consortium. And it makes it challenging to discuss the different domains without having a common language about these domains. So I will make it very simple and try to explain the basics of the idea. First of all, often we have a structural model to analyze a structural behavior. And the structural model, as it was asked by George, it can be derived from a BIM model. It's BI model, so a building information model, depending in what details and exactly what is the resolution and the type of the BIM. But just to present, this is an architectural plan, or 3D plan. Sorry, just a minute. Let me switch on the pointer. So this is an architectural plan of a building, and we don't need the whole building. We only need the load-bearing parts, load-bearing elements of the building. So this is what a structural engineer would need. And all the rest is just we need this as an information of the weight on these load-bearing elements. So we have a structural model coming from the geometry and material properties that we need to be able to simulate how the structure behaves. Geometrical properties that can come directly from the BIM. And we also need some assumptions for the modeling. How do the different elements connect? We need to have some details of the structural connections. For example, it can be stored in a photo and then an engineer knows how to model it. But there are many simplifications and assumptions that we have to take when we model a building. Another part is the loading. What affects what will happen with the building, like what is the weight on the structure. There can be some wind load or snow load or temperature change that can also affect the behavior of the building. What we get from a structural model is we get its structural response. Now, these are some of the properties that an engineer would be interested in, such as displacements, how the structure is displacing, what are the strains, what stresses appear in the structure, and normally with a conventional designing process, what I would need to check is to get the worst scenario, what could be the load on the structure, and the worst scenario that my material properties as bad as could happen. And then I want to see that the biggest stresses in the structure will not be bigger than what the material can resist. If I'm looking at the dynamics of the structure, I can also check velocities, accelerations, and just to, it's not showing how the model itself is behaving, but I can also check model properties that you saw that these are some characteristics of the dynamic behavior of the building. And this is something that we can measure as Uros presented it. Now, what will be the task of what we would try to achieve is the following. It could be that I want to improve my structural model. For example, I want to improve on those modeling assumptions that I made. And I want to improve it such a way that I want to use measurements on the real structure. So on those one of those responses. Or it could be just simply forgetting about the structural model. And this is what you see here in the errors, that all these different inputs of the structural model are in some level uncertain. We never know their exact values. And because of that, the output, how the model will behave, also has some uncertainty. So our main goal is to try to shrink these uncertainties to be able to prognose or predict how this structure is going to behave. So is it the arrow? Okay. So what first I'm going to explain is how to make, instead of the structural model that we have, how to make a purely data-driven model. So you can hear from machine learning models recently a lot, I think, but just to explain in a rough way. So let's suppose that we can actually measure the loading, what is influencing the structural behavior. And we can also measure the structural response itself. Let's say we can put some sensors on a bridge or on a building and measure the displacements or measure the strains, what's happening with the building. Or measure the eigenfrequencies and the eigenmodes, how Uros explained it. And now we can derive a model which is purely data-driven. It's a mathematical model which takes as input these measurements of the loading conditions and takes as output those structural responses. So I don't exactly like this approach, and I will explain that later why. But mainly we are dropping away all this engineering knowledge that we have about the physics of the building and the material and so on. And instead we just let a machine learn it by itself how the structure behaves. You have to know that with such method, I can only know how the structure behaves under loading that the measurements show. So, for example, I would need at least a year of observation to track how the weather is changing, the temperature is changing, to be able to follow and train a model that it can learn how the structure will behave. Good. Okay, so I'm saying I will follow a machine learning approach. I have some inputs, I have some outputs, and I want to train a model to learn a function that takes these inputs and recovers those structural responses. The main problems that can appear with machine learning methods is, this is a graph which is cited from the work of Microsoft Research about explainable boosted machines. And what this plot shows is that there are different approaches how to, or ways to do machine learning models. For example, you can have decision trees and naive bias based method that are quite simple methods, but the problem that when the problem is very complex, I cannot really build a function which is generalizing enough with these simple methods. Why it's written, it's intelligibility. It means more like interpretability, how much the model can be interpreted. So with the easy, simple models, it's easy to explain what the model did, what is behind, what the model is doing. I'm taking a certain input and I can see the machinery, how it becomes the output. And this way I know what the model does more or less. And then I can improve these models with more sophisticated models, such as deep neural networks or gradient boosted decision trees that are on this upper corner, which means it really becomes a black box model. You don't really understand what's happening with the input because the structure is so complex that it's difficult to explain why this specific input resulted in a specific output. And it's a black box model, you cannot see it, but they can work quite accurately. Now, there are many efforts recently in the machine learning community to do something with this lack of interpretability. And one way is, for example, where the plot was cited from, is to use explainable boosted machines. So have a specific structure of the machine learning model to make it somehow interpretable. Another way to do it is to add on top of these deep neural networks or on some tree methods, some explainability model, a special or additional model that explains the model itself. Now I can talk about two different explanations. I can talk about global explanations and local explanations. So global explanations would be answers to general questions like which input parameter is influencing the most my displacements in this specific element, for example. And the local explanation would give me explanation on a specific measured value. This is the value that I measured, and this measurement was different from the expected value of the measurement because of which features, which input parameters. So this is what we are trying to do with the help of the recently published papers, how to, for example, use SHAP analysis together with decision trees. And I promise that this will be the only equations in this only slide. So I won't do many equations. I just want to show that these are those input parameters that are, for example, the loading parameters on the structure, the wind load, and if it's a bridge, the load coming from the traffic, or it could be earthquake load as well. And my output is how the structure is behaving, for example, a displacement, or it could be the eigenfrequency of the structure, or it could be strains or stresses, which is not very common to measure. And what I'm trying to do, I'm trying to map from X to Y with the function F. So this will be my machine learning model, which takes the X and maps it to this Y value. And the way I'm trying to do that in a general case is to minimize the mean square error on the training points that I have. With the help of the SHAP analysis, how I change this map is to write it in a form where I can attribute the output to the different features. So you can see that this first value is directly the expected value of the output. So the average displacement of a beam, for example. And then there's a second part, which is only due to the specific input parameters. So I can say that I measured this displacement, and I know that I subtract the average displacement that's actually happening on this beam. And then I can say that in addition to the average displacement, the displacement increased because of, let's say, the wind load, and it's decreased because of the temperature change, just as an example. And I can also write other terms like coupled terms or higher degree terms, where the influence is due to a combination of change of input parameters. So this is the idea of making an explainable model. And such way, this is an example for a bridge that is in Slovenia that we did together with ZAG and with the Ljubljana University, is that in this example, what we measured was the frequencies of cables, of pre-stressed cables. And here you can see the global explanation model. So what was the most important input for the eigenfrequency of the cables? And in this case, it was the temperature change. So the biggest percentage of the change of the eigenfrequency of the cable is due to the fact that the temperature is changing all the time. You can also see some other weather parameters like UV radiation and solar radiation. They are highly correlated with the temperature. So you cannot really distinguish within these correlated input parameters, because they depend on each other or they are correlated with each other. And it's not specifically showing causality, but these parameters together are responsible for the frequency change. You can also see the speed of the wind. I think we also had as a categorical feature the direction of the wind or the different traffic loads. And this is how the model that we could train can be explained in a global way. In a local way, it can be also explained. You can see that there was one specific measurement of eigenfrequency, which had a value here. And you can see that the temperature in general, when the temperature has a reddish color, it means that its value was high. Then it shifted the eigenfrequency in the negative direction from this vertical line, which is the expected value of the eigenfrequency of the cable. So you can specifically see how the different measurements were attributed to the different input parameters, which gives a nice support for us, for example, to extract some effects. If we want to get rid of the weather effects, we can subtract this from the prediction model. And what you see here is just the real signal that we didn't use for the training, the sensor data. And the blue line is the prediction of how the frequency will change. And you can see that we can pretty well predict the behavior of the structure. And this is only from the weather effects. And you can also subtract these weather effects and get the change in between the two. So just one slide. This was when I have a purely data-driven model. And what I prefer is to combine our engineering knowledge together with the data that we can observe. And I think this is what's leading us really to a trustable digital twin model. So you can imagine any simulation here, not just a finite element simulation that is simulating the building, but it could be any other simulation, like a simulation of the building physics of the building, like how the isolation is effective to increase energy efficiency, for example. And let's say there are those uncertain input parameters here noted, like Q1, Q2. You can imagine these are two inputs of the structural model. It could be material properties or modeling coefficients or anything. And then you have an output, which is how the structure itself is behaving. And I can measure how the structure itself is behaving. For example, I can check its eigenfrequencies and mode shapes, what Uros explained how to do it. And what I'm trying to do is it can be described in two phases. First, I call the forward model. How do I get from the parameters to the responses? And this is a conventional computation, so it's not a big challenge now for engineers to do it. What is the challenge is to take into account the uncertainty of these input parameters. And if you take into account this uncertainty with specific methods that I'm not going to detail today, you can easily quantify the uncertainties of the response itself. How sure are you that the structure will behave like that? And then the second phase is called the inverse method, when you can learn also about the response of the structure. And what you would try to do is to shrink these uncertainties. And this is with the Bayesian framework done, to be able to shrink these uncertainties, still keep it in a stochastic fashion, so not in a deterministic fashion, but to have a distribution of these input parameters instead of one deterministic value. So you start with some uncertainty, you can measure the response, and then you can update this. And I will give the word for Blaz to explain this, how this is done in more detail.
Thank you, Noémi. So Uros first explained about how to get to the experimental data. And now Noémi explained first how to use this data to generate models, only data-driven. And now she began to explain how we can improve our models, our numerical models, using this experimental data. And I will continue on with what she already began. And I like to motivate this presentation with the example that we've been working on, and that's tall timber buildings. And one of the challenges of tall timber buildings is vibrations, and more specifically, those are wind-induced vibrations. They're not dangerous to the health of the structure, but they are uncomfortable. So we like to avoid those kind of vibrations. And to do that, we would like to, in advance, know how to predict model properties before the building is built, right? So if we know that there will be problems in wind, we can solve it before with the design. So how to do those accurate models that I talk about? We do our work on already built buildings, so existing buildings, and we analyze those buildings. And this is done in 3 steps. The first step is to create the initial model. This initial model is done with finite element models, with commercial software, using all the documentation that we have on that building. And this is our best engineering judgment prediction on model properties. And this is also what design practitioners can do. And at the end, what we get is model properties. Those are natural frequencies and mode shapes, about which Uros talked about. And then in the second step is to do experiments on the building. And what we do is we put the shaker on top of the building. We shake the building in one direction and in the other direction, and we measure accelerations throughout the building. And then with model identification, we obtain model properties. So we have on one hand initial model properties, and then on the other hand, we have measurement model properties. And we trust the measurements more than we trust the model. So what we do is we change the initial model so that it better replicates the measurements. And this is the process that is called model updating. And first, what we do is we just manually change the model, but then we do it in automatized way. And this automatized way of updating the model, that's what we call model updating. And today I will specifically talk more about the Bayesian model updating. So that's a probabilistic one. And I'd like to explain a little bit about the methodology, how this is done. So very simplistic way of explaining what the model is just, black box model where it takes some input parameters and gives you an output parameter. In our case, if you have tall timber building, maybe input parameters might be some material properties of timber. Maybe it's density or some stiffness parameters. And what the output is maybe natural frequency. This is what we talked about, natural frequencies or mode shapes. And because we don't know what are the exact values of material properties, we maybe have some idea what would the right values be. Maybe we know that for density is 450 kilograms per cubic meter, maybe it's 370 or maybe it's 500, but we know that it's not, 800 or 100. So we have some idea about the probability distribution, and that's why we transform our model into probabilistic view. And each input parameter has then assigned probability distribution. And this distribution reflects our knowledge about the parameter, and it reflects the uncertainty that we have in this parameter. And this uncertainty then propagates through the model. So also our outputs can be viewed as random variables, and they have some uncertainty ascribed to it or calculated. And this is the confidence that we have in the model. So one thing that we can do about this probability distribution of an output is we can quantify it. So with the uncertainty quantification, we analyze what is maybe mean value of the probability distribution, or what is variance, or some other statistical measures that we can perform. And if the variance of an output is large, then this means that we don't have so much confidence in the output. And what we would like to do if the variance is large, we would like to reduce it. So I'll talk about how we can reduce it. But first, I like to speak about some other analysis that is possible to be done, and this is sensitivity analysis. So we'd like to analyze how different input parameters contribute to the variance of an output. So if we said that the variance maybe is too large, then we can analyze, well, how do different input parameters contribute? And maybe we realize that it's x3, the parameter that contributes the most. So those are the parameters from which we will gain the most reduction of the variance. And those are the parameters that we should try to fix or to reduce their variance. And if parameter, maybe parameter 3 would be density of timber, what we could then do is measure the density of timber. What we could do is take some samples of timber and measure it, and we could fix the value of input. But the problem in the building is that we cannot just take samples from the already existing building. This would be an intrusive method. So what we can do is not measure the inputs, but we measure the output, the natural frequencies. And then in the process of model updating, and more specifically Bayesian inversion, what we do is we infer back from the experiments done on the output, on the natural frequencies, we infer back about the input parameters. And so using Bayesian theorem, we employ information about prior knowledge about those input parameters and the information about outputs to get updated values of updated probability distributions of input parameters. And those probability distributions are then called posterior distributions. And they teach us about what those maybe as-built characteristics of a building are. And on one hand, they teach us about how to better model the building next time, but they can also be used in maybe damage detection. I think that's what the next presentation will be about. And of course, making our models more accurate. And for all those three analysis that I showed you, so uncertainty quantification, sensitivity analysis, and Bayesian inversion, those are stochastic methods, which means that they need a lot of evaluations of the model. So what we then do, because this model might be computationally expensive, we try to substitute it with the surrogate model, which computes the response within milliseconds, and then we can do our analysis more efficiently. So that's our presentation as in a simple way. We try to explain it, and yeah, we're open for questions.
Thanks, Noémi and Blaz. We have a question from George Dorzanos. He asks, in which ways this type of analysis is benefited or beneficent by DBL? Probably the core idea is to use the data loader in DBL to train the ML models. Will the results of the analysis be stored in DBL? Maybe Noémi can explain this.
Yeah, sure. So when we worked on these projects together with University of Ljubljana and ZAG, we found that this different type of analysis can be extremely useful for built structures. And because many engineers were very interested in our analysis, we decided to go for a larger project to make this more usable in a way. And one of these options to make it more usable is to tie it to the digital building logbook. It will be an application or several applications that engineers can access. So there is all these linked data, which is linked to the digital building logbook, like the beam of the model or different designing models, for example, that the engineers used, and we can build on top of that with the help of the Buildchain platform, a platform where the measurements can be stored. And for example, if I can see that other people's measured another timber building, then we can derive more general conclusions. So this will be one of the pilots, for example, in the Buildchain project. When we have two similar buildings with similar materials, but they are relatively new concepts, we can see how the design procedure could be changed. And this can be achievable by having access to these different measurements, so that we don't have to replicate all these measurements, because now I would like to learn about timber buildings and I do not know that other people did these measurements. Then I can directly pull it from this platform and access this data or purchase this data to be able to learn more about this specific type of buildings, or it could be about specific type of connections. Another thing that you can do with, for example, purely data-driven models, I said one of the advantages that you can subtract different effects, but you can also check how your prediction of structural behavior is changing from the actually measured structure. And when you see a significant change in between the prediction model and the true structure, then you should suspect that either your sensors went wrong or something went wrong with the structure. And then it can send an alert to check what's happening with the sensor. And maybe there should be some maintenance jobs to do to prevent disaster, for example. So there are many applications and use cases that actually we are working on to make a list of simple sentences how the different actors, the stakeholders around the digital building logbook can benefit from such tools and platform. That's the idea. I hope I answered your question. Sorry, not my question.
I get a message that somebody would like to answer the question live, but I have no idea how to allow this.
Yes, there's one more question that arises by Mohammed. So Mohammed is thanking for a great presentation, and he has two questions regarding the measurement aspect, and in particular artificial vibration induced. Which directions are considered? Lateral, longitudinal, or both of them? And another question regarding the model parameter learning. Did you try testing methods like evidential regression learning for uncertainty quantification in order to learn the parameters of multiple models distributions?
Okay, so the first question about the vibrations induced is directed to me. Yes, so we shake in the two lateral directions of the building, not in longitudinal, and from that what we obtain is at least 3 modes of vibrations, but in one case we could obtain also 8 modes of vibration. And we see that the more modes that we can measure and match with our model, the better the procedure, the better the results of model updating. So that's for the first question. And the second question,
I'm not exactly sure if I understand well the question, but for example, we have this toy structure that Uros presented, where we will try to demonstrate all these different functionalities that we will provide. And there we do consider different models. So you can also have different models and do, with the help of Bayesian updating, model selection. So that can be also an option. I don't know what you mean about multiple distributions, but we have like several parameters that are considered, and there's a prior distribution which represents the engineering knowledge, all the information gathered in a form of probability distribution. So our prior knowledge defines the prior probabilities of the parameters. I'm not sure what you mean about multiple distributions.
maybe it's multivariate.
But it is definitely multivariate, and we can also consider stochastic fields. So not only specific parameters, but also field values. Like you can also identify a stochastic field, such as like a moduli can be changed throughout the spatial domain, and then you can locate corrosion, for example, or a structural weakness. So these are things that we can also do and provide. Evidential regression. What evidential regression is?
No.
We can use regression for making the surrogate model. We use regression for the purely data-driven method too in some of the examples. I would need your microphone to be able to know what you exactly mean. But I hope at least most of the questions had an answer.
Yes, thank you both for your question, for your answers, and for your presentations. Now we have a final presentation of Professor Pietro Croce from the University of Pisa, who will talk about structural health monitoring. Please, Professor Croce, it's your floor.
Thank you very much, and I am starting. I hope you are. It's okay. You are. You can see my screen, Bostjan?
Yes, it's perfect.
Okay, perfect. Thank you very much. Good morning, everybody. This very short presentation is dealing with the first part of real-time monitoring of structural infrastructure and historical heritage. This is the first part of a larger presentation, which will be the subject of further webinar. And the aim is to discuss the approach to be followed in designing the monitoring system, in particular, particularly focusing on conception and setup. In this first webinar, I will focus on the calibration of a finite element model, which is the bell tower of the St. Nicholas Church in Pisa, which is a very important historical monument. It's a bell tower from the 11th century. And in the next webinar, I will, my intention is to illustrate a relevant real case application regarding the San Domenico Basilica in Siena and control and the monitoring of the remote monitoring of the after collapse remains of the Persevera Bridge in Genoa. What is the aims of real-time monitoring? Some of the objectives have been illustrated by our colleagues in the previous presentation. We have the assessment of the structural response and this variation over the time, or especially dealing with the study of evolution over time of existing crack pattern, interpretation, diagnosis, and prognosis of crack pattern, structural damage and deterioration. Also, in view of definition and prioritization of the intervention, assessment of information in comparing the structural response before and after some kind of intervention, the calibration of numerical model and finite element models through operational and experimental model analysis, definition of alarm thresholds for management of early warning procedure, and so on. In designing the monitoring system, we should consider several aspects. We should define the particular aims of the monitoring. We should identify the relevant parameters to be measured, displacement, rotation, velocity, acceleration, temperature, and so on, in such a way that to identify the number, the type, the location of the sensor, the architecture of the system, and its accessibility. If we, in fact, we can have local instrumentation, or we can have remote controls. We can have monitoring real time or by spot and so on. The data, and at the end or during the monitoring, one of the most important aspects, which has been very well described by my colleagues in the previous presentation, is the aspect regarding the elaboration of data and the analysis of data itself. Another aspect which is very important is the sample rate of which allows to, depending on the number of reading per second, to assess dynamic behaviors of the structure or not. And clearly this relevant activity should be addressed on the case-by-case basis. Looking at heritage structure, considering the Venice Charter and the Vittoria Falls Charter, which is especially devoted for structural study, for structural assessment and structural intervention, we can have a very, very complicated decision-making flowchart for heritage structure, where monitoring is a very relevant part. My intention is not to go too much in detail about this aspect, but who is interested can refer to the bibliography. Other practical issues which are closely connected with the monitoring and the issues in designing the monitoring system are the different legal system in different countries, the fact that use, inspection, and maintenance of structure are controlled by the owner, so that in many cases the system, the monitoring system cannot be controlled during the life of the structure, and it is very difficult to define it during the design or the execution phase. And as I already said, we have two main aspects. Well, from one side, we have the interpretation or the real-time interpretation of the result, which is a very challenging aspect. The definition of alarm threshold in case the monitoring system is intended to be used for early warning procedure. And another extremely relevant aspect, when the monitoring is continuously running, is the obsolescence of the instrumentation, which makes the instrument itself, the sensor itself, very obsolete in few years. Another aspect which is very relevant is that monitoring cannot replace or cannot always replace the intervention. It's just to make a very important example, you can see here in a severe crack pattern which appeared in 2005 in two arches of an historical masonry bridge in Mulazzo over the Magra River in the northern part of Tuscany, crack pattern due mainly to the scour of the piers. you can see that immediately after a special monitoring system was installed by the authority, but the result was in any case that due to the lack of intervention during the flooding of the Magra River in 2011, 2 arches collapsed, and they were substituted in order to allow the light, at least the light traffic, by a Bailey Bridge. A first relevant example of the aim of monitoring system is, as already said by our colleagues, is the calibration of finite element models. These examples concerning the bell tower of San Nicola Church. You can see here the bell tower, which is included in the walls of the adjacent building and of the adjacent convent. And one of the most relevant problems in defining a dynamic model of this bell tower is difficult to model the contact between the building, the tower bell and the adjacent building. You can see here the finite element model of the bell tower, which is very accurate. It's made by thousands and thousands of elements. And I'm sorry, this, okay. And in order to calibrate the model, the dynamic, it was studied the dynamic response of the structures using different kind of excitation. As already said, often we use environmental excitation because they are vibrations induced by traffic or by wind are always present. In case of bell tower, often we use the bell oscillation as source of excitation, so we have periodic excitation. But in that case, we use also for this very massive structure, which cannot be excited in relevant extent by the first 2 sources of excitation. We use also impulsive excitation with a very peculiar instrumented hammer. In this case, we have a loaded lorry, which is running on the street and very fast, and then a step that you can see here induce an impact of the lorry on the street, and consequently it excites the bell tower. The problem is that in this case, due to the particular geometry of the particular situation of the bell tower, we discovered that not that a specific excitation is not able to excite all the relevant mode shapes due to the difficulty to transfer the vibration to the structure. You can see here the typical time history of the structural response in terms of induced by environmental excitation, by periodic excitation, and by impulsive excitation. You can see that the order of magnitude is very significantly different. And also for the analysis of the signal, we use different techniques. We use a fast Fourier transform, also with the windowing technique, as well as the wavelet transform, due to their different sensitivity and to the different ability to detect the frequency and the consequently in the model shape. You can see here the spectra obtained using by different technique for environmental excitation, for periodic excitation, and for impulsive excitation. And you can see that, generally speaking, in this case, the wavelet transform was much more selective than the fast Fourier transform in identifying the eigenfrequency of the structure. You can see, as you can see, in fact, looking at the table, you can see that environmental excitation was not able to detect the first two modes of the structure. The Bell excitation, so the periodic excitation, was able to detect the first two, while the impulsive excitation was able to detect almost all the techniques. And you must also consider that the second mode, which is parallel to the reference direction, which is the axis of the San Maria Street, which is where the bell is prospecting, are detected only using the periodic and the impulsive excitation, because probably due to the fact that the bell tower is connected with the walls of the adjacent buildings. As the result of calibration is summarized here. We have the elastic modulus and the specific weight, which allow to match the response of the finite element model with the experimental one. And what is important is the equivalent stiffness of the convent walls, which was necessary to model in order to catch also the natural frequency and the modal shape of the second frequency. You see in this final slide the comparison between the natural frequency experimentally detected and the natural frequency derived from the calibrate finite element model, and at the end of the process, it was possible to have a very good agreement. Thank you for your attention.
Thank you, Professor Croce. Now the paper is open for discussion, or the presentation is open for discussion. At the moment, we don't have any question, but maybe I can ask you, for the first example that you showed with those arcs, did the sensors that were on the bridge were able to detect something, that something was wrong when the cracks appear, or
on the tower? You mean on the tower, on the bell tower?
No, the bridge with the arcs. So if you have sensors on the bridge, did they detect that something was wrong when the cracks appear in the arcs?
For what I know, because I was not involved.
Mm-hmm.
Fortunately, I was not involved in the monitoring. I was involved in the improvement of the bridge at after the collapse, but not in the before. Fortunately for me. And they put on the ash. They measure displacement through or crack opening with the deformometers, and also there were some accelerometers.
Mm-hmm. Mm-hmm.
So in principle, they were able to detect some vibration. But the problem is that, in my opinion, it was a lack of interpretation of the interpretation of the real causes of the cracking, because it was clearly due to the scour of the piers.
Mm-hmm.
And so looking at the shape of the crack, at the shape and at the relevance of the crack, it was clearly due to the scour of the pier.
Mm-hmm.
And the question was that during the monitoring, there was a small movement of the crack until the flooding arrives, and when the flood arrives, it was the scar becomes more important, and the bridge and the pier fall down, inducing the collapse of two arches. I must also say that after the collapse, we studied very well the bridge, and we after the consolidation, we published also a paper about it. It is very strange what happened when the bridge was built in the second half of 19th century. The level of foundation was different from one side to another side, because at that time the bed of the river was mainly displaced toward the Villafranca side, the bridges between Villafranca and Mulazzo. During the years, the bed was changing, moving to the Mulazzo side, so inducing more relevant scour in the piers at Mulazzo side, where the foundation were less deep.
Mm-hmm. Thank you, Professor Croce, for this explanation. I think we are in position now to close this webinar, this Buildchain webinar, which was related to the structures. I would like to thank all the participants. There were many of them. And I would also like to thank the presenters who made nice presentations, and I hope that the participants get some new knowledge about the modeling and experimenting with the structures.